If we think about this random play against always rock, isn't it kind of odd that this gives us an even chance to win, lose, or tie? Because we would think that if our opponent was always playing rock, we would absolutely dominate that person. Because we would say, hold on a second, you're going to be always rock, I'm going to be always paper. Well, the reason for this is we have a more adaptive strategy. The strategy that we have is one that's going to notice this person really seems to like throwing that rock shape. I'm going to start throwing that paper shape. We can come up with a strategy that is responsive to what the other player does. And so, if we wanted to extend this code to involve strategies which try to beat the last thing the other person played, well, we'll see there is some value in having set up the structure of the game with these two dictionaries, because we can say that beats last play, given the last thing that they played, just looks up in whatever is beaten by the last thing that the other person played. Now, of course, if we're at the very beginning of the game, there is no last play. So at the very beginning of the game, I just might throw something randomly. I really have no history to base this off of. And if I make that change, one unfortunate consequence of this is not only do I have to include it in my list of all the things that I'm going to build these scenarios out of, but I also have to pass in, well, what the last play was, even if it's not used by these strategies. So you can see that the logic for these two strategies has now gained an extra argument, an underscore to indicate that it's not being used, so that this function can gain an extra argument that it will use, an argument representing what the last thing the other player played. Also note that this logic here that was originally 2 lines of code now has to be written as 1 line of code, or I have to be a little bit careful. Of course, I have to identify that at the very beginning of the game, we don't know what the last play is, so those will be none values to indicate nothing has been played just yet. But if I write this in the style that it was originally written, where I had 2 lines of code, note that there is a very subtle error here. And the subtle error here is the challenger can actually see what the player just played. And so, well, what I really would need to do is I'd need to write this a little bit more clumsily like this to represent the last player and the last challenger, and to distinguish that from the current player's play and the current challenger's play, and then I have to do something like this, and that would be correct. Otherwise, if I were to not make that change, and that would be very difficult for me to spot, this would of course be erroneous because the challenger strategy could now be responsive to the player strategy. This basically means the player is just a little bit quick at the draw, throws their shape, and the challenger goes from that rock to that paper or that rock to that scissors in milliseconds before finalizing their shape, which of course we know is not allowed in tournament rock, paper, scissors. Beyond that, however, we seem to have a pretty interesting and pretty useful piece of code because we can now define strategies and see how they play out. Does beats last play actually do better? Well, here, if we have beats last play against beats last play, you can see they get into this cycle where they're just beating each other, so they tie. But beats last play against always rock does exactly what we expect. It dominates. If you are always rock and that other person is doing a beats last play, they're going to be throwing paper every single time, maybe except for the very first time. Of course, do note with the random seeding here, I think the first move is always a paper. If we change this very slightly, you can see, you tie basically 0% of the time, but then you dominate the other person 100% of the time. And so we get results that are interesting and are expected. What happens if we have more sophisticated strategies? For example, strategies that are parameterized. Well, why do you only like rock? Why can't you also like scissors or paper? So why can't it be that instead of there being an always rock, there's an always shape that's parameterized on what the shape is? Here you can see I have a function that dynamically defines a function. And when I set up my scenarios, I set up 1 for rock, 1 for paper, and 1 for scissors. We won't expect anything that interesting to come out of these. Honestly, always rock, always paper, always scissors should all behave identically, but there may be some other strategies like a bias strategy that biases towards paper, rock, or scissors that might then behave slightly differently against these always one shape. The downside here is all of these are probably either always paper against always paper, always rock against always rock, or always scissors against always scissors, or the variation where it's rock against paper, rock against scissors, but I can't tell. And my output here, which is just looking at the name of these functions, makes it really difficult for me to identify which one of these it is. Now, I could, of course, do something like this and change the name of this to something always, and here we could do shape.name.lower, and that might help a little bit. Python functions can be renamed. So here we go, always rock. Okay, that makes sense. Always rock against always scissors means you win every single time. Okay, I can read that output. Or another option I could do is I could take these parameterized strategies and I could specify them statically, not dynamically. That is, instead of specifying them as part of my scenario setup, I could specify them at the module level. And I could use this dynamic definition of a function as a helper for me to define always rock, always scissors, and always paper. But then if this is a module that somebody's importing, they don't have to then go through the same always shape, pass in shape.rock. They could just import always rock, always scissors, or always paper. And this mechanism here is really mostly used for my purposes. I might even put an underscore before the name of it to indicate that this is really for internal purposes. You're really only supposed to use these 3 specific variations that I have. And here you can see I've even renamed them. Beyond those kind of strategies, what if I wanted strategies that had some other knowledge? Some other knowledge of something that's happened in the game beyond what the last play was. For example, I want a strategy that plays some kind of pattern. This is something that people might discover. If you're doing beats last play, could I come up with a pattern that every time you're trying to beat the last thing I play, I actually think ahead and I play whatever you're going to lose against and lock you into a cycle where you're just going to be dominated because you think I'm going to play rock, so you play paper, but I actually play scissors. And then you think that I'm going to play scissors again, so you play rock, but I actually play paper, and I lock you into this cycle where I'm outguessing you. I'm thinking one more step ahead. Well, if that's the case, I could set up my pattern, and I could just go through my pattern, but I have to know which round I'm on. Because otherwise, these functions really don't have any sense of the overall global tournament style of the game. They don't know that we're in round 3. They don't know that we're in the 3rd step of this game. They only know what the last play the other player had was. And since we don't know what the other player's strategy is, we can't use that to determine anything. And so what we might need to do is create another argument that we pass into our strategies, here the round number. So we identify that we're in round number 0, 1, 2, up to round number 9,999. And in each of these strategies, we just add in another argument that we don't do anything with. And we could specify this with a double underscore like this, or we could even do something like this and say this takes some number of additional keyword and positional arguments that you don't do anything with. The downside here is it's very likely to be the case that we came up with pattern play after already doing quite a bit of analysis with these strategies, and the requirements for pattern play, that we know what round we're in so that we can index into our pattern at that particular stage of the pattern, is then causing us to go back to a bunch of code that we already wrote or that maybe other people already wrote and update it. And this is always difficult because you never want to tell somebody that the code that they wrote that worked for a long time needs to be written so that it can handle something that doesn't bring any value to them, but brings value just to you. Everybody hates it when they upgrade to a latest version of some library and the library authors say, you need to rewrite all your code that's been working for the last 5 years. But as a consequence of rewriting it, all you get in exchange is your code doesn't fail anymore. It's not faster, it doesn't have more features, it's not more fluent, it just is allowed to continue to work. And this is the unfortunate consequence of having to add these extra arguments. And so it may very well be the case that even though this is a valid thing that we want to model, this is the wrong way to go about modeling it. Instead of modeling this as some extra argument that we pass into the function, maybe we can keep the signature of these the same, where they just know what that last play is, and they still have some arguments that they ignore. And instead of modeling these as stateless functions, we model the pattern play as some kind of data class, some kind of stateful entity and instance of a class. And in this instance of the class, we could set up a live iterator that cycles through the pattern, and we could just call whatever the next thing in, whenever we call this thing as a function, we can always just get whatever the next thing out of that iterator is. And implementing in this fashion, we could see how pattern play plays against beats last play. If the pattern is rock, then scissors, then paper, and we'll see that this particular pattern absolutely wipes the floor with beats last play because, of course, they think you are always playing rock, so they play paper and you play scissors, which beats their paper. So they say, oh, you're playing scissors. And so they play rock, and then you beat paper, which beats their rock. And then you kind of lock into the cycle where you're always one step ahead of them, outguessing them. Now, it's probably the case that I want to take this framework and start implementing more and more and more strategies to see, are there other types of patterns? Are there adaptive strategies? Are there strategies that can bait somebody into thinking that it's always rock? Is there a strategy like beats-last-play that can say, do I think they're playing this strategy? And if so, what's my counter strategy? We'll want to come up with very sophisticated variations of these. And in order to do that, we'll define a brand new function, or we could define a class, or if we wanted to try something even more sophisticated, we could define a coroutine. Whatever the case may be, we'll define that and then we'll add it to our scenarios. But it's kind of a pain that every time I define a new strategy, I have to add it in this main logic to all the scenarios I'm playing. Could I programmatically register those scenarios? And in fact, this might be a good place for me to make use of another part of Python, the use of decorators. Here, I'll write a decorator. And the decorator specifies variants of a particular strategy. So random play has only one variant. That is just the random play variant. Always shape has 3 variants, one that is always rock, one that's always paper, one that's always scissors. Beats-last-play only has 1 variant. And our pattern play has this one variant, the rock, scissors, paper pattern play. We can come up with other patterns and see how those patterns play against each other. Our decorator will just take the variant specification that we have and the function and populate a global list with each one of those. That global list will be populated with these strategy named tuple objects, and these are just going to allow us to call what the underlying strategy is with some intermediation to specify what that variant does, some extra arguments that are passed into that variant, and allow us to programmatically identify what all of our combinations are, which means now, if we wanted to implement one more strategy, like another variation of this, here let's do a rock, scissors, scissors, paper. It's pretty easy to do this, and we don't have to change our main logic. Or if we wanted to define a brand new strategy, well, here we'll do one with no variance. We can just do that, and then we can just populate this with the variants that we want, and it'll automatically be picked up by our simulator and run. So we can avoid fiddly changes that occur down here. Now, this may be one other motivation why we might want to go even beyond that data class modeling for maintaining any sort of history to maybe a coroutine modeling, in part because that can then further limit the changes that we might have to make to this main loop so that our analytical code stays the same, and we can then iterate on brand new strategies. But that brings us to a very sophisticated implementation of a very simple game of rock, paper, scissors with the ability to model and analyze how strategies do against each other. Note, the resulting code that we ended up with was very sophisticated. It made use of all sorts of Python features like decorators. It made use of features like named tuples and data classes. It made use of additional syntax in Python. And it was much more sophisticated than our naive approach. However, every step along the way, the sophistication was motivated by a tangible outcome of that sophistication, something that we got out of it, and weighed against, is it really worth it or not? Is this a mistake that I'm likely to make? And if so, is this something that I want to protect against? The expert's approach to rock, paper, scissors is not to write that final version of the code instead of the very first version of the code. An expert's approach may be to skip past some of the very naive initial versions to something that's a little bit fancier than just a function that prints things out to the screen. But the expert's approach is one in which every time we introduce some additional sophistication, we motivate it, we justify it, we say this gives us real value, commensurate to the amount of additional complexity or difficulty to understand or additional mechanism that it introduces into our code. It gains us something that we can then use to accomplish something more sophisticated or more in line with whatever our business requirements are. Thank you all for joining us for this session on rock, paper, scissors. I hope you're looking forward to our upcoming sessions on simple word games, as well as our session on Battleship, where we'll look at how an expert might approach these very, very simple problems and make use of all of the richness of Python and the sophisticated approaches that we have in a measured, justified approach. Thank you all for joining us, and I'll see you all next time.